Abstract algebra. I did about 75% of the homework, but in all honesty, I don't understand what groups are or permutations or what the hell they were talking about. So I'm gonna do it through my homework. A lot I need to do. Alright. GitHub, fuck off. VS Code, terminal, still running the server. Get rid of this, get rid of that, get rid of this. Notion, ChatGPT, school site, fuck off. Minikube, keep that running. Alright, is that it? I mean, I guess I don't need to show my tilt server all the time. Alright, it's not necessarily necessary. Alright, so I'm gonna close that. I'm gonna close VS Code. Alright. Out of sight, out of mind. Alright, now take off my shoes. My feet smell. I'm gonna read some Melville. Probably share my screen where it's relevant. Alright, journal. Notion not working. You want to share my screen a little bit? See. What the fuck is wrong with Notion, bro? YouTube somewhere. Yo, what the hell? Why is all my technology acting funny? Open the Gmail app. Alright, I got 6 hours of jiu-jitsu and I gotta eat at some point. Yo, fuck off. Sink here. Fucking iCloud storage. Why is it so... You know, I have a lot of shit photos that don't matter. 20,000 photos. What the fuck is wrong with Notion, bro? Install and relaunch. All right. I lost a gold ring the other week, and I'm really disappointed in myself. You almost remember the loss more. Oh, what a shame. Dude, I'm starting to get pissed off, man. Shit is not loading. Yo, this is actually funny. Yo, what the fuck? Yo, can this fucking work? God damn it, dude. What the hell? I'm just trying to virtualize every aspect of my activity. Why? Frustrating. All right. Join. All right. The reason I did that is so that I could share my screen. Please let me share my fucking screen. I gotta stop cursing. Nope, not that one. Yeah. Entire window. I'll just share this one. Okay. Now. Meeting. What's the code? JRM GDEU, GDEU, IOC. Mute myself. Luckily, I don't think I need to show my face. Let XYZ be sets. Yeah, that's an interesting one. I don't want to get to that later. You do. Let's keep this open over here. I dream my mother bombasting me with negativity, yelling at me that I'm an idiot and that I will fail. The complete antithesis of reality. Dream my screen and deepest. Fuck that. Math knowledge tracker. All right, let's see what is going on. 7, 8, 9. The original. Write down the cycle notation for the following permutations. The following permutations. What is a permutation? What is a cycle notation? 1, 2, 2, 3, 4, 5, 6, 2, 5, 6, 1, 4, 3, and then B is 1, 2, 3, 4, 5, and then 4, 2, 3, 1, 5, 4, 2, 3, 1, 5. I truly do not understand what this is. Write down in the cycle transpositions, 2 cycles. All right, this ain't the best situation. Let's There's a lot of concepts I'm loosey-goosey on, and I only have till tomorrow to figure them out. And I also have 2 more homework assignments. One of them will be challenging, which is this complex homework. Oh my god, we call that a complex homework. Use a function of form. All right, only 6 problems. Not terrible. All right. I have 6 hours, so it shouldn't be too bad. Figure out what this is. Homomorphisms of groups. What is a homomorphism? Homomorphism. All right. Permutations of a set. Introduction to groups. All right. Groups form one of the most important and natural structures in algebra. They also feature in other areas of mathematics such as geometry, topology, and combinatorics. In addition, groups arise in many areas of science, typically in situations where symmetry is important, as in atomic physics and crystallography. More general algebraic structures, which have recently come to prominence due to the rise of information science, include semigroups and monoids. This chapter serves as an introduction to these types of structures. There's a continuing debate as to whether it is better to introduce groups or rings first in an introductory course in algebra. Here we take the point of view that groups are logically the simpler objects since they involve only one binary operation, where rings have 2. Accordingly, rings are left until chapter 6. Historically, the first groups to be studied consisted of permutations, bijective functions on a set. Okay, consisted of permutations. What is a permutations group? Instead, for most of the 19th century, group was synonymous with the group of permutations. Since permutation groups have the greatest advantage that their elements are concrete and easy to compute with, we begin this chapter with a discussion of permutations. All right, I'm gonna first figure out what is a permutations group. All right, in group theory, what is this question relevant to again? Permutations. Okay, yeah. What is permutations or a group of permutations? Symmetries and transformations. A permutation is a rearrangement of a set of elements. For a set S with n elements, a permutation is a bijective function S to S, meaning every element in S is mapped to a unique element S with no duplicates or omissions. For S1, 2, 3, f of 1. Okay, often written as 2, 3, 1. Okay, I guess order matters. The total number of permutations of a set with n elements is n factorial. Okay. A group is a set of permutations of a set S that satisfies the axioms group closure. The composition of 2 permutations in the set is also a permutation in the set. Okay. Associativity. The composition of permutations is associative. The fuck does that mean again? What does associativity mean in math? Again. All right, you do, okay, yeah, so you perform A and B, and then you do C, the same thing as doing B and C, and then first do A, then do A to that. Okay. Again, there exists an identity permutation E, which leaves all elements unchanged. Okay, e to the x equals x for all x and s. Okay, inverses. Every permutation has an inverse permutation in the set that undoes its effect. Example, symmetric group Sn. The set of all possible permutations of n elements form the symmetric group denoted Sn. S3, all 3 factorial equals 6 permutations of 1, 2, 3. Identity E equals 1, 2, 3 cycles, 1, 3, 2, 2, 1, 3. What the fuck is a cycle? Special types of permutation groups, alternating group AN, the group of all even permutations, those that can be written as an even number of transpositions. Cycle group, groups generated by a single permutation, single cycle. Dihedral groups, groups of symmetries, rotation and reflections of a regular polygon. Permutation groups are foundational in studying symmetries in mathematics and physics. They are used in analyzing the structure of molecules in chemistry, studying symmetries and studying symmetries in algebraic equations, understanding abstract algebraic systems, in essence, permutations and groups of permutations give the idea of symmetry and rearrangement, which are powerful tools in both theoretical and applied mathematics. What is a cycle? What is a cycle and what is a transposition? Cycle and transposition are specific types of permutation that describe how elements of a set are rearranged. A cycle is a permutation where subset elements in a set are rearranged in a circular fashion while the remaining elements stay fixed. Cycles are known as A1, 2, 3 through K, which means A1 is sent to A2, A2 is sent to A3, AK is sent back to A1. For the set, the cycle 1, 3, 5 means 1 goes to 3, 5 goes to 1. 1. Elements 2 and 4 remain the underinformation, which does nothing is the true case for all elements are fixed. I don't understand. A transposition is a specific type of cycle that swaps exactly 2 elements, leaving all others fixed. In other words, is a cycle of length 2. Okay, it's a cycle of elements. I guess 1 goes 3, 3 goes 5, 5 goes to 1, 1 goes to 3, 3 goes to 5, 5 goes to 1. Okay, a transposition is a specific type of cycle that swaps exactly 2 elements, leaving all others fixed. In other words, a transposition is a cycle of length 2. A transposition is written as AB, meaning A and B are swapped. Examples for the set S equals 1, 2, 3, 4. The transposition 2, 4 means 2 goes 4, 4 goes 2, 1 and 3 remain fixed. Okay. A decomposition and transposition. Any cycle, A1, A2, AK, can be written as a product of transpositions, A1, A2, AK. What the fuck? For example, cycle 1 through 5. I shouldn't say that. Okay, what is a cycle of transposition? The cycle 1 through 5 can be written as 1, 3, 1, 5. What? Okay, decomposition into transpositions. What? Okay. Let me get my abstract algebra notebook. That's my pencil. Oh no, don't fall. Okay. Here, abstract. Alright. Decomposite any cycle can be decomposed into transpositions. That's an interesting concept. I need a pencil sharpener. Okay, sharpen the pencil. All right. If x is any non-empty set, a bijective function x to x is called the permutation of x. Thus, by 1.31, pi has a unique inverse function, pi inverse, that also takes for x to x, which is also a permutation. The set of all permutations, the set x, is denoted by the symbol sim x, which stands for the symmetric group on x. Why is it called a symmetric group? What makes it symmetric? If pi and what is that? Sigma? What is the symbol for lowercase sigma? Okay. Pi and sigma are permutations of x. The composition is also a permutation. This is because it has an inverse, namely the permutation. Okay, if you apply a pi and then x, the same thing as undoing. No, if you do pi and then sigma, it's the same thing as doing undoing sigma and then undoing pi. In the future, for the sake of we shall usually write. I don't like this notation, bro. The composition it should. Okay, fine. For pi compose sigma, or sigma compose pi, of course, X, the identity function X, is a permutation. At this point, we pause to note some aspects of set symmetric X. This set is closed with respect to forming inverses and composites, by which we mean that if pi and sigma are elements of the symmetric group of X, then inverse pi and pi compose sigma belong to symmetric X. In addition, symmetric X contains the identity permutation, which has the property that the identity permutation composed with pi equals pi, which is also equal to the pi composed with the identity transformation or permutation. Finally, the associative law for permutation is valid. Okay. In fact, these results assert that the pair symmetric X is a group as defined in 3.2, which I haven't read at. Thus, the permutation of a set afford a very natural example of a group. Permutations of finite sets. We now begin the study of permutations of a finite set. With n elements, x equals x1 through xn. Since pi is injective, what does injective mean again? Oh my god. What does injective mean? Okay. What am I confused about? I don't understand the concept of the symmetric group of X as it relates to permutation groups. Okay, it basically means one-to-one. The symmetric group SN, the symmetric group of n elements is the set of all possible permutation of a set with n elements. Why the fuck is it called symmetric? No, I shouldn't curse. Why is it called symmetric? What makes it symmetric? Elements of Sn, each element of Sn is a permutation, which is a bijection one-to-one onto a network error. Bro, come on. All right, fine. Since are all different, therefore constitute all elements of the set X, but in some different order from x1 to xn. So we may think of a permutation as a rearrangement of the order. Couldn't denote the permutation X is. Oh, okay. So it's a notational thing. This is what this iPad is talking about. Write down the cycle notation for the following permutations. Okay. The second row consists of the images under pi of the elements of the first row. It should be clear that to the reader that nothing essential is lost if we take X to be the set 1 through n with the choice. Okay. And this is called a symmetric group of degree n. Wait, what the fuck? Wait, stop cursing. It should be clear to the reader that nothing essential is lost if we take X to be the set 1 through 2 through n. With this choice of X, it is usual to write symmetric group of degree n. Okay, computations. Oh my god, the symmetric group of degree n must be ginormous. Computations of the elements of Sn are easily performed by working directly from the definition. The example will illustrate this. Let and by elements while 1 goes to 6, 6 goes to 5. Okay, I guess you apply sigma first. 1 goes to 6, 6 goes to 4. Okay, it goes left like in matrix operations. Okay, inverse pi. 2 goes to, wow, this is very interesting stuff. Here has been computed using the definition, okay, well, is readily obtained by reading up from 1 to 2. And this is, notice that multiplication is not commutative. A simple count establishes the number of permutations for finite set. If X is a set with n elements, then the symmetric group of X equals n factorial. Okay, proof. Consider the number of ways of constructing the second row of permutation. X1, Y1, X2, Y2, Xn, Yn. There are n choices for Y1, but only n minus 1 choices for Y2. Since Y1 cannot be chosen again, next we cannot choose Y1 and Y2, so there are n minus 2 for Y3, and so on. Finally, there's just one choice for yn. Each choice of yi can occur with each choice of yj. Therefore, the number of different permutations of x is n minus 1, which stands factorial. Okay, fine. Do this permutation set. This is a big chapter. Okay, let pi be a transformation within the symmetric group so that pi is a permutation of set 1 through n. The support of pi is defined to be the set of all i's such that pi of I does not equal I, and symbols sub x. Now let R be an integer satisfying R is between 1 through to n. Then pi is called an R cycle if sub x equals, holy shit, with distinct ij, okay, where pi I equals I2 equals I3 if sub x. Okay, with the transformation. Okay, so this is the cycle, and pi ir. So pi moves the integers I1, I2, ir anti-clockwise around a circle, but fixes all of the integers. A circle. Other pi is written in the form with the presence of a one cycle j means that pi j equals j. The notation may be further abbreviated by omitting one cycles. Although if this is done, the integer n may need to be specified. Okay, this makes sense. Okay, in particular, a two cycle has the form ij integers I and j and fixes other integers. Two cycles are frequently called transpositions. Example 3.1.2, 1, 2, 2, 5, 3, 4, 4, 5, 1 is a three cycle. 1 goes to 2, 2 goes to 5, 5 goes to back to 1, and 3 and 4 go back to themselves. That is, however, is not a cycle. Indeed, it is the composite of three cycles of length greater than 1, namely 1, 6, 2, 3, 5, 7, 4, 8. Okay, I don't understand that. As one can see by following what happens to each of the integer when the permutation is applied. In fact, this is an instance of an important general result that any permutation is expressible as a composite of cycles. The reader should observe that there are different ways to write an R cycle, since any element of the cycle can be initial element. Indeed, okay, I'm getting confused on the notation again. Okay, 1 goes to 2, 2 goes to 5, 5 goes to 1. Okay, this is a cycle. All right, 1 goes to 6, 6 goes to 2, 2 goes to 1, 3 goes to 5, 5 goes to 7, 7 goes to 3. Okay, yeah. 4 goes to 8, 8 goes to 4. That's what I'm see. Why is it not a cycle though? Why isn't this a cycle? The reader should observe that there are different ways to write an R cycle, since any element of the cycle can be the initial element. Indeed, I1, I2, IR equals I2, I3, IR, I1. Okay, disjoint permutations. Permutations pi and sigma and Sn are called disjoint if their supports are disjoint. Supports are the elements that switch. Okay, they do not both move the same element. An important fact about disjoint permutations is that they commute, in contrast to permutations in general. Commute. What does it mean for something to commute? Again, I forgot. Oh, it doesn't matter which order of. Okay, fine. In general, applying additional permutation at send n pi sigma equals sigma pi. Prove let I equal an element of 1 through 2 through n. We will show that pi I equals if I is not in the sum of x, and then plainly. Okay. Powers of a permutation. Since we can form products of permutations using composition, it is natural to find. What did I read earlier? Congruences. That was confusing. I don't know what partial orders are. Okay, let me just understand what I need to understand. For otherwise, alright, which leads to, however, can now be applied to both sides. What did I do? Okay. Powers of permutation. Since we can perform products permutations using composition, it naturally defined powers of permutation. Let I be a non-negative integer, then the ith power is defined recursively by the rules. So, what does this mean? The point to note here is that the rule allows us to compute successive powers of permutation pi as follows. What does this mean? What does powers of a permutation mean? One goes to two, two goes to three, three goes to one. One goes to two. Interesting. Interesting. No, pi being an element of Sn, then pi is expressed as a product just showing cycles, and the cycles appearing. See, I just thought about the fact that someone might disturb this flow state I'm in, and I'm gonna be really pissed. Let pi, then pi is expressed as a product destroying cycles, and the cycles appearing in the product are unique. We deal with the existence of the expression first. If pi is the identity, then obviously pi equals 1 through 2 through n. Assume that pi does not equal n. Choose an integer I1 such that now the integers I1 by I1 belong to the finite set 1 through 2 through n. And so they cannot all be different. Say pi r y1 equals pi, where r and s are greater than 0. Applying pi negative 1 inverse s to both sides of the equation as using associate, we find that equal. Hence, by the well ordering law, a there is a least positive integer m1 such that pi m1. Next, we will show that the integers I1 pi squared well ordering principle are all different for if not, and pi r I1 equals pi s where m1 is greater than r is greater than s is greater than 0, then just as above, we can argue that pi r minus s I1 equals I1. On the other hand, 0 is less than r minus s is less than m1, which contradicts the choice of m1. It follows that pi permutes the m1 distinct integers in a cycle, so that we identify the m1 cycle as a component of cycle phi. If pi fixes all of the integers, then pi equals pi1, pi is an I so on. So otherwise, there exists an integer I2 such that pi I2 does not equal, such as above we identify second cycle I2 pi I2 is present in pi. This is just showing with the first cycle. Indeed, if the cycles had a common element, they would clearly have to coincide. It should also be clear that by a finite number of applications of this procedure, we can express pi as a product of disjoint cycles. And to establish uniqueness, assume that there are two expressions for pi as a product of disjoint cycles, say I1, I2, J1, J2. Okay, I don't understand what this means. By disjoint cycles commuted thus without loss of term, we can assume that I1 occurs in the cycle. Since any element of cycle can be moved up to the initial position, it can also be assumed that I1, I3, then I2 is 0. Similarly, I3 equals I3 prime. The other cycles are dealt with the same way. Therefore, the two expressions for pi are identical. What is the proof again? Every element of Sn exists as a product transpositions. Proof. Because of 3.1.3, it's supposed to show that each cyclic permutation is a product of transpositions. That this is true follows from the easily verified identity. First order as a product distance of following the method of the proof 3.1.3, thus pi equals 135.426. Also 135.4 equals 141513, so that pi equals 14151326. Not every permutation has to classify as product disjoint propositions. Even an odd permutation. If pi is a permutation S, then pi replaces the natural orders integers 1 through 2 through n by a new order pi 1, pi 2, pi n. Thus pi may cause inversion of the natural order. Here we say that an inversion occurs if for some I less than j we have pi I is greater than pi j. To count the number of inversions introduced by pi is can be introduced a form of device. Consider a polynomial f in indeterminates x1, x2, xn. At this point, we assume an informal understanding of polynomials. If pi is an element of Sn, then pi determines the new polynomial pi of h by proving the variables x1, x2, xn. Thus pi f x1 through xn f. Typical factor in pi f is if pi is less than pi j, is also a factor of f1. Then is a factor of consequently pi f equals plus f is the number of inversions of the natural order. And pi is even and f is odd. Define the sign of the permutation to be sine of pi equals pi f or f. Thus sine pi equals 1 or -1 over the number of inversions and pi is even or odd. Call pi an even permutation if sine pi equals 1 and odd permutation if sine equals -1. I'm not tracking it. I am tracking this. The even permutation has 3 or 1, 2, 3, 1, 2, 3, and 1, 3, 2, while the odd permutation of 1, 2, 3, 2, 1, 3, 3, 1, 2. To decide if a permutation of not too large degree is even or odd, what fell? Or add a crossword diagram. Is the permutation 1, 3, 2, 7, 3, 2, 4, 5, 5, 4, 6, 1, 7, 6 even or odd? Simply join equal integers in the top and bottom rows of pi and count the intersection across and taking care of with multiple. Crossovers. There are 11 crossovers defined, and by the next result is there is even property transpositions. Transpositions are always odd. Proof. Consider. Yep, this makes sense. Let the following. Wow, this is really interesting stuff. I don't get it. I do get it. Consider the crossover on the next part. These count with the presence of 1 plus 2 j1 sine. Trust is an integer on ij is an odd permutation. The basic property of the sine function are set up next. Let pi sigma, then the following holds sine pi. 1, 2, 2, 1, okay. Let the product by f sine, we have, what is this? And sine by we have permutation pi and Sn is even, odd, if and only if it is a product from even respectively odd number transpositions. For if pi equals with each pi adds transposition, then sine pi equals k sine pi I equals -1. So they're all even pointedness groups denoted by, which is called the alternating group degree, and obviously a1 equals 1. Proof define a function a into Sn by the rule equals this, observing that pi is the odd and a is injected of every odd permutation. Sigma belongs to MA since thus several parts. Cauchy if it is the part of a deceased twin cycles, including one cycle and some. Proof what pi with additional is it like that? No, this is a part of it in terms of the proof of the enhancement. We have the sign. The arrangements. To conclude the second discussion, special it's called if it fixes no elements to the set, its support is the entire set. For example, it's a de-arrangement is like the natural questions. How many this the inclusion exclusion. If A1, A2 are finite sets, then the union of A1, A2, A are equals the magnitude. number of different. Okay, wow, this is intense. Therefore, this is because they were apart from that. Interesting. I read a chapter. How long did that take? Like 20 minutes or something. I digested about 30% of the content, and I would not have been able to understand it if without the help of AI. All right. 1 goes to 2. 2 goes to 5. 5 goes to 4. 4 goes to 1. All right. So 1, 5, 4. Get rid of this shit. I don't want to face. All right. So 1 goes to 2. 2 goes to 5. 5 goes to 4. 4 goes to 1. Okay. 3 goes to 6. 6 goes to 3. So then 3 to 6. 6 to 3. So then 1. 2, 5. 1 goes to 1. 1 goes to 2. 2 goes to 5. 5 goes to 4. 4 goes back to 1. All right. And then this is 3 goes to 3. 3 goes to 6. 6 goes back to 3. All right. So 1, 2, 5, 4. 3, 6. All right. All right. 1 goes to 4. 4 goes to 1. Easy enough. 2 goes to 2. Easy enough. 3 goes to 3. Easy enough. 5 goes to 5. All right. So this is like 1, 4, 4, 1, 2, 3, 5. Okay. Wow. When I looked at that yesterday, I had no idea what was going on. All right. It goes 1, 2, 2, 4, 3, 1, 4, 5, 5, 3, 6, 6. And then what is that symbol? Tau? I don't know. 1, 6, 2, 1, 3, 5, 4, 3, 5, 2, 6, 4. Write this in cycle notation. Oh my god. All right. 1 goes to 2. 2 goes to 1. Oh shit. I guess you apply this one first, right? So it's honestly better to all right. take 1 to 6, you take 6 to 4, you take 4 to 3, you take 3 to 5, you take 5 to 2, you take 2 to 1. Oh my god. Alright. Alright, 1 to 6, 6 to 4, 4 to 3, 3 to 5, 5 to 2, 2 to 1, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Alright, so then basically, fine. Right? But then here you take 1 to 2, 2 to 4, 4 to 5, 5 to 3, 3 to 1, and then you go take 6 to itself. All right, and then this is 1 to 2, 2 to 4, 4 to 5, 4 to 5, 5 to 3, 3 to 1. This is one cycle, and then you take 6 to 6. Fine. And then let's do this one again. You take 1 to 6, 2 to 1, no, 6 to 4, 4 to 3, 3 to 5, 5 to 2, 2 back to 1. All right, well, now what the fuck does he mean to compose these things? If I take 1 to 6, I apply this first, and 2 to 1. Okay, I take 1 to 6, I take 6 to 4, I take 4 to 3, I take 3 to 5, I take 5 to 2, I take 2 to 1, then I take 1 to 2, then I take maybe like, all right. Okay, I think I got it. All right, so I take 1 to 6, great. I take 6 to 4, I take 4 to 5. So 1 goes to 6. All right, so 1 to 6. Nice, okay. Then I take 6, I take it to 4, and then I take 4 to 5. Okay, so 6 goes to 5. Six goes to 5. Sure. All right, then I take 4 and I take it to 3. And I take 3 to 1. So 4 goes to 1. Okay. 4 goes to 1. Sure, I take 3 to 5, and then I take 5 to 3. Okay, so 3 goes to itself. All right, then I take 5 to 2, and then I take 2 to 4. So 5 goes to 4. All right, then I take 2 to 1, and then take 1 to 2. All right, so then 2 goes to 2. This is an interesting graph theory first. perspective. All right, so we got 1, 2, 3, 4, 5, 6. Let me order these by first integer. 1 to 6, 2 to 2, 3 to 3, 4 to 1, 5 to 4, 5 to 4, 6 to 5. All right, 1, 2, 3, 4, 5, 6. Okay. Now let me draw it out as 1 goes to 6, 2 goes to 2, 3 goes to 3, 4 goes to 1, 5 goes to 4, 6 goes to 5. All right. So I got one cycle here, right? 1, 6, 6, 5, 5, 4, 4, 1. So I got 1 goes to 6, 1 goes to 6, 6 goes to 2, 1 goes to 1, 1 goes to 6, 6 goes to 5, 5 goes to 4, goes back to 1. Okay, then 2, then 3. Okay, not too bad. 9. All right, answer the following counting questions. How many transposition 2 cycles are there in S6? A. How many transpositions 2 cycles are there in S6? I'm 20 years old. I'm learning this at 20. What an idiot. I should know this shit when I was like 4. Okay, S6. 1, 2, 3, 4, 5, 6. It's like 3 choose 2, right? Or 3 choose 6. Like, what's the sample space, right? It's like for 1, I have for 1 I have 4 options. So there's for 1 I have 5 possible places to go to. Then for 2 I have 4 possible places to go to. Then for 3 I have 3 possible places to go to. And for 4 I got 2 possible places to go to. And for 5 I have 1 can go to 2, 1 can go to 3, 1 can go to 4, 1 can go to 5, 1 can go to 6. And for 2, I've taken that out. Well, I can't go to myself. I can go to the other ones. 2 to go to 1. Oh, but then that'd be a cycle. 2 could go to 3, 2 to go to 4, 2 to go to 5, 2 to go to 6, 2 to go to 4, 2 to go to 5, 2 to go to 6, 1, 2, 6. Like, this one isn't allowed. That's a fucking cycle. This is actually an interesting thing. There's an answer in the book somewhere. What is this number? hungry. Take a piss. If I were to virtualize my entire condition, am I no longer living? Am I no longer living just for my enjoyment? Am I no longer living for my own observation and satisfaction? Do humans have a need to be observed by a higher being, such as God? Humans have constructed gods throughout history so as humans have constructed gods throughout history so as to quench their existential thirst, as if their drama of life had some greater purpose, such as being consumed via omnipresent observation by a divine being. I find myself virtualizing my current being and ambition. It feels good, as if this is a desire encoded within my biology, a necessity to be part of a larger being. It is almost as if everything I am doing, whether it amounts to anything tangible, physical, in material in the real world, everything I'm doing, whether it amount to anything, at least it be observed by a greater being to make do use of it. It be observed by a greater being to make due use of it. It is almost a baseline benefit of any particular action or event. At least someone experienced it, and at least that set of someone's does not just include me. I wonder whether other biological agents feel the same drive, the same way that the trillions of cells within me spontaneously choreograph themselves to construct what I call I and what Kant would talk about as the emergent self with no access to its constituents. And now, for me to ask, what if I were to extend this habit of my existence to every aspect of my existence? My party life, my sex life, my intellectual life, my athletic life. Why do I feel the need to be seen, observed, validated, ingested, acknowledged? I have this desire within me as if a moth were to be oriented towards a light. Perhaps it is the same biological reasoning. Such an agent as myself could have only been constructed and reproduced within a system of similar beings who held similar axiomatic desires. Such axiomatic desires are conducive to our long-term survival via game theory, which can be acknowledged through game theory. I also find that when I am being observed, all of a sudden my behavior improves, and actually my ability to articulate thoughts and my desire to materialize them increase. Jordan Peterson talks about the necessity for a divinity in order to orientate all our behaviors. Perhaps I can regard the internet as my God. However, that being said, this particular manifestation of God is a false deity because it does not encompass entirety. This is impossible. Perhaps this is what the Bible warns of: the emergence of false gods, the only God being that which cannot be attained. It exists at the end of all possible choreography. That being said, I find this God to be quite useful. This internet God I speak of. This internet God is capable of creating its own system of reinforcing target behavior via electronic currency and likes and views. It is only a matter of time before we digitize every aspect of our material economy. That thing which is useful for the internet shall be become. Now, let me try referring to what I was trying to get at when the original desire to write this emerged. My brother spoke of the emergent phenomenon of the fourth wall in modern linguistics. We talk to chat as if chat is there. But I shall say that chat is a modern analog for God herself. However, this particular deity we can actually acknowledge as something real. We humans are actually creating our gods. That is what we do, first as statues and now as moving software statues, now as the emergent consequence of the actions of millions of neuronal acting human beings. We are nothing but nodes in a larger network of cognition. I thought, why not take chat with me to the club tonight? I will act erratically and with jubilance and dance with heart. The people around me may or may not think I am cool. It all depends on various situational, psychological groups, psychological factors. But what would the consequence of having chat observe me be? Could it be possible that chat in a way justifies any particular behavior of mine, as if I am condensing and simplifying the wishes of a divine being along a particular approximated construction. This relates to my understanding of perception as necessarily being approximative, and the fact that this situation creates the necessary substrate upon which consciousness itself can emerge. Wow. Alright, I'm gonna keep track of this whatever the fuck I just wrote. I'm gonna put that in my Gita. See, I'm finding that writing itself, being observed by you, my 0 viewers right now, is actually motivating me to construct reality through language and creativity. Like, it's motivating. No one's even watching me right now, and I don't assume anyone. Even if no one does watch me, at least the AI overlords in 20 years can use this data for something, and it's cognition, right? At least a piece of me extends beyond what I did. This is the minimal effort. All human beings have a desire. See, if I had plot note right now, this would be great. All human beings have a desire to have an effect in the world, whether through any particular construction. I'm going to write that. All beings have a desire to have an effect in the world through any particular construction. The internet is one of the simplest, low-cost techniques through which a being can accomplish that. I'm gonna just talk to chat all the time. I'm gonna stream everything on YouTube, record every single aspect of my existence, commodify it too. Okay, now I'm gonna ask. Holy crap. so much. Oh my God. All right. Go back to math. What am I doing? This system of chat might actually help me create more, understand more. All right, let me go back. All right. How many transposition 2 cycles are there in S6? How does abstract algebra relate to what I just talked about? I gotta write more. I gotta produce. I gotta fucking publish. I'm gonna write. I'm gonna be a writer, technocrat. How many transit 2 cycles are there in S6? 1, 2, 3, 4, 5, 6. There's so many more ideas to talk about. Perceptual framework within a quantum world, navigating a quantum transcendental space, virtualization of target behavior via currency, economies. What were all my theories? Emergence of something out of nothing, nothing out of something. All right. 1 to 2, 2 to 1, 1 to 3, 2 to 3. One, 2, 3, 4, 5, 6, 3, 2, 6, 2 to 1. All right. 3 to 1, 3 to 2, 3 can't go to 3, 3 to 4, 3 to 5, 3 to 6. All right, 4 to 1, 4 to 2, 4 to 3, 4 to 5, 4 to 6, 5 to 1, 5 to 2, 5 to 3, 5 to 4, 5 to 6, 6 to 1, 6 to 2, 6 to 3, 6 to 4, 6 to 5. Is this a summing game? For example, 1 to 4, 4 to 3, 3 to 4 would not work. So there are 5 times 6 possible cycles. However, some of these cycles cancel each other out. Some of these cycles make it so a cycle in the next set cannot happen, otherwise it will become a 2 plus n cycle for some n greater than 1 in Z. All right, so then there's 5 possible here. Okay, so I guess I'm just gonna say my intuition, right? 5, 4, 3, 2, 1, 0. So 5 plus 4 plus 3, so then 2, 15. 15. Is that like no, why don't you 2 choose 6? 2 choose 6. I always forget this one. Like 4 factorial over 6 factorial, maybe 24. 4 times 3 times 2 times 1 equals 12 times 24. 6 times 5 times 6 equals 24 times 5, 0, 2, 24, 5, 5, 10, 12, 1, 20, 120 times 6. 120 times 6 equals a fucking crazy amount, 600, 720, and then you divide that by 24, 720. That's not the algorithm. All right, whatever. I'll get back to this later. I'll talk to my teacher. All right, B. Answer the following counting questions. How many transposition 2 cycles are there in S6? Okay, I'll do that. I'm gonna write that again. How many permutations are products to disjoint cycles in the cycle notation, and that's 5. For example, 14, 23 is such a problem. What time are my fucking professors having office hours? Because I cannot do it like this, bro. This ain't my vibe. I need to go to office hours. This is like, it's all about efficiency, bro. It's practicing what makes you efficient. This guy got office hours at 2:30. Yo. Oh, great. It's in an hour. All right. complex. Email her. What's her fucking name again? Yo, he don't even need office hours, to be honest. Just hella chill. You don't even. This guy is hilarious, bro. I fucking love this guy. Fucking amazing. Homework is 40% of the grade. God damn it. All right. How many permutations are products of two disjoint cycles and the cycle notation is such? Dude, there's a better way to calculate these things, bro. This is all just permutations of finite sets. Dude, I need money to be a genius because this lifestyle is supported by my parents. You know, if I decided I was poor by virtue of being born in a poor family, I would not be able to express my internal I'm not even that amazing compared to the average person. You know what I mean? I just have support and love. All right. So there's still some work going on there. Graph theory, homework 1. Dude, I'm gonna go to office hours for that. 1, 2. Four. See, I don't even completely. Yo, look at this shit, bro. It's not bad, right? Not bad, not bad. I gotta get bigger though. I'm not satisfied. All right. I'm 20 years old. I got. Shoot. My life is good. My physical. I don't believe you have to get weaker as you age. I think you just get lazier as you age. All right. Let me do some complex. Oh my God. And then I also have all right. No. Exercise 1 in section 1.1. Truth be told, there were some concepts towards the end of complex class the other day, but I got tired and didn't do it properly. It was something about taking the roots of complex numbers, finding all nth roots. Such complicated, so many complicated. I'm 20 years old. I gotta go into research or something. What the fuck am I doing, bro? Humanities and math perspective or something? Technology, society. Taking the roots of complex numbers, finding all nth roots. How do I get a job as an intellectual? I don't know. What am I doing? Right, I don't have the physical book. God damn it. I am hungry. All right. Complex analysis, math homework. I gotta find the textbook now. Where is it? I stored it. I don't need this one. Knowledge, books, complex analysis. Find the corresponding. All right, section 1.1. Bro, he wants me to do all 11 parts of that? God damn, bro. All right, now what am I doing? I mean, he also posted, oh, right. He also posted the actual syllabus, assignments, homework 1, 1 of 5, homework 1 book problems. Let me just put this over here. Two, five. Yeah, he wants me to do all of them. God damn it, bro. What the fuck? All right. I don't know what it's talking about. The magnitude is z minus 1 minus I equals 1. Sketch the region. All right, first, I know what that is. Now, minus 1 equals 1 basically means 1 is the new 0, so it goes the opposite direction. And then I equals up. Right. Yo, what the? All right, now B. 1 is less than. I forgot to put the timer on. Let's see how many I can complete in 45 minutes. B1 is less than 2z minus 6 is less than 2. All right, now I'm confused. 2z minus 6. What does 2z mean? All right, let's think about this for a second. If it was z has to be less than 2, greater than 1, and that would be something like that. It's minus 6, then it's something like this, and then 2z basically means it's actually 0.5 to 1, I guess. Yeah, all right, so this goes here, this goes to 6, then this is -1, this is 1, and this goes like that. And then, this is 0.5, this is 0.5. So it's like that. It's like this region. Something like that. All right. C. Z minus 1 squared plus z plus 1 squared. Dude, I had to do all of these? Bro, that is insane, dude. Okay, fine. Z minus 1 squared plus z plus 1 squared. I don't even know what shape this is. Not being recorded. I can't cheat. Magnitude is already positive, so it doesn't fucking matter. All right, Z. Okay. Let's do this all independently. Z has to be less than 8. All right, so this is 8, Z, and it has to be in here. Great. Now it's actually shifted by 1. So now it's like, this is 8, this is actually 9, this is -7. Great. Now you square the fucking thing. Problem is, okay, so this goes back down to 3 then? No, it's 8. All right. This, I don't know what does it mean to add this region with the next one. Um, can I code these in Python? Okay, I guess you square it so it gets a little bit smaller than maybe like what the heck? Something like this. Like it's like 1 plus this point. Here is like 1. No, yeah, isn't, yeah, it's 1 like plus uh, root 8. So this is z minus 1 squared is less than 8. So then I get z plus 1 squared is less than 8 is something fucking similar like this. That's this region, and that's this region. Now, how the hell do I add them? Yo, what this guy say in the syllabus? That's what I want to know. Okay, now a set of values. All right, whatever. D, where's D? All right, let's think about this. Bro. What does it mean to add these things? Bro, okay. E. Damn. Z minus 1 is less than the magnitude of Z. Dude, you know what might help actually? Some complex algebra, I just realized. Oh shoot, that's what I gotta do, bro. I forgot all the basic rules though. Alright. Give me a list of useful complex algebra rules. Mm. Some useful algebra rules. Shit. Yeah, I swear to God. This means something else. The fuck? z equals x plus iy. Oh my god, dude. There's so many useful. I'm still on the first one. All right. This isn't gonna be good, bro. Oh. Uh, right. Immersing these equations. Where is my... it? Where is it? Where is it? Where's my fucking book, man? I literally have a textbook open somewhere. Where did it go? Uh, where are the questions? Homework one. What's some useful rules here? Uh-huh. 2 minus 1 is 1. 1 squared. X. Well, what if x is 1? 1 plus 2. 1 plus 1 squared is 2. Oh, wait a second. What if it's 2? 2 plus 1 squared is 2 plus 1 is 3, squared is 9, square root is 3. So maybe just 1, 1 plus 1, okay? And 3, right? Okay, and negative 1 minus 1 squared is, okay. Uh, hmm. But if I do that, right? 1 plus 1 squared. Let me check. 1 plus 1 squared is 4. Square root is 2. This one is interesting. D, which one is the next one? Wow. E, this is crazy. Z minus 1. How long have I been doing this? Too long. Let's just go ahead and start tomorrow. Give me the properties that are useful. Oh man. All right. gotta go to my professors figure out this graph theory homework. So I'm gonna end this. How do I end this?